Hi there, Physics 152. Welcome to the 9th practical out of 10. So next week's our last one. This week you'll be doing two theoretical activities in which you will be looking at two-slit interference. And then you'll be analyzing some data that I'll be taking right here, right now. So you may have heard that light can be modeled as a stream of particles called photons. So this is a laser, which has the property that it is monochromatic, meaning that it's exactly one color, and color corresponds to wavelength. So what we say is that all this laser light, every photon in this laser light has a wavelength which is the same and corresponds to this red color. And now I also have this double slit pattern. So there are two vertical, so there's an opaque barrier, which is silvered, and then cut into the opaque barrier are two parallel vertical slits. They each have a width of 0.04 millimeters, measured horizontally, and they are spaced half a millimeter apart. And I can block this laser beam with the slits and allow the light to pass through the two slits. The other thing I can do is I have a metal plate which I can block the slits if I want to turn it off, or I can slide it carefully over and just let the light from one slit laser through one slit, and then two slits to open it and one slit to close it. So let's turn off the lights and do the experiment. Okay, so I'm starting with it blocked, and let's carefully open up just one slit. There we go. Okay, so that is called a single slit interference pattern. I believe it's discussed in your textbook in section 33.4. You can see a big wide central maximum stretched out horizontally, so it gets spread out parallel to the width of this slit. That 0.04 millimeters has spread it out horizontally. And then there's a dark patch there, and then you can kind of see on either side a little bright bump again, and then it gets dark again. So that's called single slit interference. Now let's open up both slits. There's the second. So now there's two slits. So it's a little bit brighter. It's twice as bright on average. But do you see the little, they're called interference fringes, these little bumps? So these little bumps, they're called interference fringes, and they are from the effect of the light from both slits interfering with one another. So I guess the dark ones go down to 0 intensity, and the bright fringes are actually 4 times as intense as the single slit pattern. So the whole thing averages out as having twice the energy of the single slit, which again looks like this. Single slit, double slit. So, so what's interesting, actually, what I like to do is let's consider this point right here that is a dark interference fringe. If I close the curtains and then close one of the slits, it gets brighter at that point. If I open the curtains, it gets darker. So the light is truly interfering with itself and causing destructive interference at a dark fringe. So now you have the data. I have included pictures from there and the measurements. The measurements here, this is 1.93 meters from here, 193 centimeters from the slits to the screen. You also have the dimensions of the slit. And you can see I've taped a little ruler here, horizontal ruler, which is measuring centimeters horizontally there. And from all this, you should be able to make a determination of the wavelength of light, both from the single slit interference pattern and also from the double slit interference pattern. And if you can measure the wavelength of something, well, it means that it definitely is a wave. So when these wave fronts hit the two slits, they have to pass through simultaneously. And what's weird is that even if you turn the light level way, way down so that individual photons are hitting here, if you gather enough photons, then you will eventually build up this, again, this interference fringe pattern, where you'll see that it's actually the probability that photons land in a bright fringe is much higher than the probability that photons land in a dark fringe. And this is also true if you use a stream of tiny electrons or even helium nuclei. So this is a quantum mechanical effect where what's interfering is actually, it's a probability amplitude, which describes how particles arrive at a detector after they travel some distance. So I hope you have fun, and I'll see you next week for our last lab.